Hi, and welcome to ECU Tuning Academy. My name's Chris, and in today's video, we're going to walk through the VE airflow strategy in Haltech NSP, focusing on what VE actually represents, how the ECU uses it to calculate airflow, and how to sanity check your numbers so you know your tune actually makes sense. We'll look at where the VE model lives inside Haltech, break down the math that happens in the background, and show how to validate VE values at idle and wide open throttle. By the end, you should understand why VE is an airflow model, not a fuel table, and why that distinction matters so much. As we go through this, I'll be navigating through the Haltech software so you can follow along on screen and mirror this on your own setup. I'll also reference concepts we covered in the Lambda video, but I'll re-explain anything that's critical. Before we jump into the software, it helps to frame the engine the right way. You'll often hear people say, an engine is just an air pump. What that really means is that if we ignore combustion for a moment, every engine cycle is simply about moving air from the intake to the exhaust. We draw air into the cylinder, close the valves, burn the fuel, then push that air back out again. If an engine were a perfect air pump, it would move a volume of air equal to its cubic capacity every cycle. So a 5.7-liter engine would move 5.7 liters of air per cycle. In reality, engines are not perfect air pumps. Restrictions in the intake, cylinder head, valves, camshaft timing, exhaust system, and even the throttle mean the engine never fills the cylinder completely. That difference between how much air the engine could hold and how much air it actually traps is what we call volumetric efficiency. So VE is simply a measure of how efficiently the engine pumps air from the intake to the exhaust. This is important because once an engine is built, most of the hardware that affects VE is fixed. What changes while the engine is running is engine speed and engine load, and those two things are exactly what the VE table is indexed by. Now let's move into the software. Go to Fuel Tuning, Tuning Method, and make sure the fuel calculation strategy is set to volumetric efficiency. This is the point where a lot of beginners go wrong, so it's worth slowing down here. The VE table is not a fuel table. It does not tell the ECU how much fuel to inject. It tells the ECU how efficiently the engine is filling its cylinders with air. Fuel only comes into the equation after airflow has been calculated. The ECU takes a few known inputs: engine displacement, manifold pressure, intake air temperature. From those, it can calculate how much air should be entering the engine. It then looks at the VE table to determine how efficiently the engine is actually moving that air at a given RPM and load. With that information, the ECU calculates the mass of air per cylinder. Once air mass is known, the ECU then uses lambda targets and the stoichiometric fuel ratio, exactly what we covered in the Lambda video, to calculate how much fuel to inject. So the correct way to think about VE is this. VE answers the question, how much air did the engine actually trap compared to what it theoretically could have? Now let's look at the table itself. Open the fuel base map. You'll see RPM on one axis and engine load, usually manifold pressure, on the other. Each cell represents how efficiently the engine fills its cylinders at that specific operating point. Lower VE numbers mean less air is being trapped. Higher VE numbers mean more air is being trapped. This brings us to the math. Although VE sounds like it's about volume, the ECU never actually works in volume. It works in mass. Air is a gas, and gases change density with temperature and pressure. That's why Haltech uses the MAP sensor and the intake air temperature sensor to account for those changes. Internally, the ECU uses a simplified form of the ideal gas law. You don't need to memorize the equation, but you do need to understand what it's doing. In simple terms, the ECU combines engine displacement, manifold pressure, intake air temperature, and the VE value. The result is grams of air per cylinder. That air mass per cylinder is then scaled by engine speed to calculate total airflow, and from there, fuel mass is calculated using lambda and stoic. So when you change a VE cell, you are directly changing the calculated air mass, not fuel. That's why VE numbers need to be physically believable. Let's look at idle first. At idle, most naturally aspirated engines will have VE values somewhere in the 30 to 45% range. Big cams may be lower, small cams may be higher, but that's a solid baseline. If your engine idles cleanly at lambda 1, but the VE value at idle is 80 or 90%, that's a red flag. The engine cannot physically fill the cylinder that efficiently at idle. Something else is wrong, and the VE table is compensating for it. Common causes include incorrect injector data, incorrect fuel pressure, or an incorrect stoichiometric setting. Now let's look at wide open throttle. At W-aught, a naturally aspirated engine will usually peak around 85 to 100% VE. A well-designed engine may exceed 100% at peak torque due to dynamic airflow effects. Turbocharged engines can show VE values well above 100% because manifold pressure already accounts for boost, and VE reflects how efficiently the engine is using that pressurized air. If a turbo engine is only showing 40 or 50% VE at full boost, but lambda is correct, that usually means airflow is being underreported and the VE table is compensating heavily. On the other hand, extremely high VE values across the entire map often indicate that the ECU is being forced to add air mathematically because one of the airflow inputs is wrong. This is where VE sanity checking becomes powerful. Rather than blindly tuning to lambda, you can step back and ask, do these airflow numbers make sense for this engine at this operating point? If the answer is no, the fix usually isn't more VE. It's correcting the inputs that feed the airflow model. This ties directly back to what we covered in the lambda video. If the stoichiometric ratio is wrong or the injector data is incorrect, the ECU calculates the wrong fuel mass. To compensate, VE numbers get pushed higher or lower until lambda looks correct. The engine runs fine, but the airflow model is no longer representative of reality. That's why VE should always be treated as an air model first and a tuning surface second. Once the airflow model makes sense, lambda control becomes easy, repeatable, and stable across conditions. A good VE table doesn't just hit lambda, it explains the engine. If your idle VE makes sense, your cruise VE is smooth, and your watt VE aligns with the engine's capability, you're on the right path. If not, the VE table is telling you something upstream needs attention. That's it for today's video. Thanks for watching, and don't forget to like and subscribe for more Haltech tuning content.